Alright, so from up there to down in here, let's get started with a quick introduction to chapter 7. First thing we're going to do is go ahead and put all of our equations together from chapters, 1, 3 and 5. And we're going to start here with what we derived in chapter 1 all the way back in section 1.9. We have the system of equations for the conservation of linear momentum, conservation of angular momentum, and the kinematic equations. So this is taken directly from chapter 1. What I've done here is just color coordinate the equations which correspond to the longitudinal sense, and also the blue ones which correspond to the lateral directional sense. So what we're going to do is deal with those separately first of all, and then look at how we go about solving them for a dynamical system. Alright, so firstly dealing with the longitudinal equations then, so the ones here in red. We're going to go ahead and replace these generic terms, the forces due to the aerodynamic forces and then the thrust forces. We have expressions for these now which we derived in chapters 3 and 5 respectively, so we're going to go ahead and replace those and try to tidy these equations up a little bit. So that's what I've done here. So I've taken the first one. So in the first equation I require fax1 and ftx. So from chapter 3, where we modelled all of the longitudinal forces and moments, section 3.7 I believe it was, where we're dealing with the small perturbations, we found an expression for fax, which was this. And then we made some assumptions to reduce this system down a little bit, and we said that these terms here were approximately 0 if we're in the subsonic region. So we're just going to assume these are 0, and we're also going to assume for convenience that we have no deflection angle of the horizontal tail. So then the second part that we need for this first equation over here is the thrust forces in the x direction. So that will come from chapter 5, right, where we modeled the thrust forces and moments, in particular section 5.6, where we derived this expression here. And again, we made an assumption about this final term here, that we can approximate it as 0. So that's what I've done, is I've gone back into chapters 3 and 5 to find expressions for these parts here, the aerodynamic and thrust forces in these longitudinal equations. I've brought them over onto this page here, simplified them with our assumptions that we've made, and what that enables us to do is replace these long expressions here into these expressions over here, where we now have full terms in here, right? So that all enables me to write this following system down here, where I'm assuming a cruise condition, so I only have a forward velocity, so I don't have a velocity component in the y or z directions. And as a result, my system of equations reduces down to this. So you can see this system here is basically the system that I started with over here, only now I've replaced the FA and FT terms and MA and MT terms into those equations over there. So that's what I've got over here, and then I can make just a couple of final assumptions and modifications to this system, just to write it in a little bit more of a convenient way. So first of all, the angular velocity component in the y direction, q, obviously we can write that as the change in Euler angle about the pitch axis. So actually this expression here is quite intuitive. So the angular velocity about an axis is the change in angle about that axis, right? But actually this is exactly what the kinematic equations told us. If we look back over to here, That's exactly what we have over here. So we're going to use that to replace q with theta dot in these equations. So anywhere that we have a q, we're going to replace it with theta dot, and anywhere we have a q dot, we're going to replace it with theta double dot. The other thing that we can do is rewrite the velocity component w, like the one that shows up here, in terms of the angle of attack alpha. Now, I've just drawn a little picture over here just to kind of make this a little bit more obvious what's going on. But if we have a vertical velocity component w, this is our u, right, in the body axis system. So remember we've rotated it for angle of attack. So that's going to be equal to VP1 because we're in a cruise condition as we set up here. So that just by applying a little bit of trigonometry to this, we can rewrite W as the sine of alpha times VP1, which is the cruise velocity. And then again, assuming our kind of small angle approximations, we said in a number of sections in the past that if the angle is small, then sine of the angle is the angle in radians, right? So that's what we're doing over here. We're rewriting the vertical component of the velocity vector in terms of the angle of attack alpha. So then if W equals alpha times VP1, then W dot is just alpha dot times by VP1. So then we can replace those parts into these equations up here. And then the last thing that we do is go ahead and introduce what we call the longitudinal dimensional stability and control derivatives. Now these are all laid out in table 7.1 of the textbook, and basically what we do is introduce these terms here for convenience in writing the system above. So you can see xu is a load of stuff here that appears in this first equation in the first term. So all that does is enable us to rewrite this mess as what we're going to call a dimensional stability and control derivative. You'll notice also in the textbook, in the table, we need to multiply out by a particular unit in a lot of cases in order to make the dimensional analysis work and to have these derivatives to be non-dimensional. So here's the full list in the table then, in the textbook. Table 7.1, you can see this is the one that I've used as an example. All of the others just come from multiplying out those equations and looking at the various terms. So all of that means is that we can write that system above there with the three different approximations that we've made here and simplifications to the derivatives as this system here. So the next thing we need to do is go ahead and perform exactly the same process on the lateral directional equations to get to the same type of system as we just found for the longitudinal equations, right? So we're going to go over here and look at the lateral directional equations, which are the color-coded blue ones, and perform exactly the same process as we've just seen. So we go back into chapter 4 this time, which was when we were modeling the lateral directional forces and moments, in particular section 4.5, where we found expressions for FAY, and we also found expressions for LA and NA, right? So again, we derived these long expressions with these coefficients, and again we were able to simplify some of these expressions with some approximations. And then for the FTY components, again they were given in chapter 5, and that was to do with the modelling of the thrust forces and moments, in particular section 5.6, and we found expressions for FTY. So again, what we're going to do is just replace these two expressions, FAY and FTY, into this equation over here, and so on and so forth for these ones as well. So that's what I'm doing over here. I'm applying the approximations that we used in that particular chapter, and all of that there, those 6 expressions, allow us to rewrite the lateral directional equations from over here as this mess. So again, we assume a cruise condition in the body axis system. That allows us to rewrite all of that in this form here. We're going to assume, for a little bit of simplification, that we're not going to have any thrust vectoring or engine out scenarios, so all of the C sub something T beta, so thrusts derivatives with respect to beta, are all going to be 0. And again, we introduce the angular velocity definitions as basically rates of change of the Euler angles in the corresponding axes. So we saw this just now for the longitudinal one, so we have the same in the roll and yaw axes as well. And then again, in exactly the same way as we rewrote rewrite W in terms of alpha, we can rewrite V in terms of beta. So we're doing exactly the same process as the longitudinal equations, but this time in the lateral directional sense. We put all of that stuff together. Again, there is a full list of these derivatives in the textbook on page 373, table 7.3. There they are, look. Full list of derivatives which allow us to simplify this expression here to get this slightly neater thing down here. The only thing I need to point out here is from now on we're going to call this ratio of these moments of inertia I1 and this ratio of moments of inertia I2. So that's where we're going to pause for a moment. So we've now got a system of equations for the lateral directional sense, and we also have a system of equations for the longitudinal sense. And what we're going to do now is to go ahead and see how we go about solving those for a dynamical system.